Whether you notice them or not, catalysts can be seen inside and outside the world of chemistry, from healing cuts or lighting matches to preventing harmful emissions from a car. It is clear that catalysts have an effect on our work environment, creating more efficient, safer methods to achieve success. Before we begin, let's take a look at 5 key facts about catalysts. So, how does the presence of a catalyst affect the rate of reaction? Catalysts provide an alternate route that requires a different activation energy, or EA, for successful collisions during a reaction. Remember, a reaction only proceeds when successful collisions between particles occur. The presence of a catalyst means a faster rate of reaction, since the particles can take an alternate route to achieve a successful collision.
Here are some analogies to help you all better understand catalysts. Suppose that a road exists between two cities. Let's call this Road A. Only the most efficient cars with the most gas will make the trip. Now suppose that a new road is built. Let's call this one Road B. Many people can now manage to get from one city to another, but the distance between the cities remains the same. You could say that the other road provides an alternate route, lowering activation energy. The original road is still there and cars can still take it. In chemistry, the majority of particles will take the path that requires less activation energy, resulting in a higher overall number of successful collisions and a faster rate of reaction. Keep in mind that the catalyst is never chemically changed nor consumed during the course of the reaction. When the reaction is finished, you would have the same mass of catalyst as you did in the beginning. Think of it like this. A catalyst is like a minister at a wedding ceremony. The minister causes the ceremony to take place, plays a role in determining how fast the ceremony is, and is not himself permanently changed as a result of the ceremony. Unlike the couple who are getting married, whose lives have permanently changed as a result of the ceremony. Ultimately, catalysts can help reduce the time needed for a reaction to occur. Its ability to withstand chemical change allows for it to be reused, making them favorable for industrial processes.
Our experiment is focused on demonstrating the effects of a catalyst in a decomposition reaction. We can demonstrate this by decomposing hydrogen peroxide and measuring its mass change as oxygen gas is released over time. Once a control is set, we can add a catalyst, such as manganese dioxide, and observe its effects on the rate of reaction. Once both experiments are done, we can compare the two values and make an assumption based on our calculations.
To conduct our experiment, you will need the following materials: safety goggles, an electronic scale, 5 100 milliliter beakers, 1 400 milliliter graduated cylinder, a pipette, 4 weighing canoes, a stopwatch, 5 grams of manganese dioxide solution, which is our catalyst, and finally 200 milliliters of 3% hydrogen peroxide.
Measure out 200 milliliters of hydrogen peroxide in a 400 milliliter graduated cylinder. Obtain 4 weighing canoes and measure 0.25 grams of manganese oxide in each. Set this aside for later. Obtain 5 100 milliliter beakers and label each A through E. For each trial, use a 100 milliliter graduated cylinder to measure out exactly 40 mils of hydrogen peroxide. Using the electronic scale, place a 100 milliliter beaker on the scale and record the initial mass of the beaker. Transfer the 40 ml of hydrogen peroxide that was measured in step 4 to the beaker labeled A. Beaker A will be the control to which no manganese oxide will be added. Using a timer, over 5 minutes, record the oxygen gas released every 30 seconds. After 5 minutes, stop the reaction and start again with beaker B. The following steps are applicable for trials B through E. Using the electronic scale, place a 100 milliliter beaker on the scale and record the initial mass of the beaker. Transfer the 40 ml of hydrogen peroxide to the beaker. Use the 0.25 grams of manganese oxide that was previously measured out and add this mass to the beaker. Over a duration of 5 minutes, record the oxygen gas released every 30 seconds. Keep watching for the remaining trials. Record all the data in the table provided. For this lab, I was able to use an appropriate calculation in calculating for the amount of gas that would be oxygen gas that would be released at completion of this reaction. So at first, I wrote down the 3% hydrogen peroxide that we used and the quantity of it, which was 40 mils. So due to the fact that 1 mil is equal to 1 gram, I knew that 40 mils was equal to 40 grams. I then multiplied 40 by 0.03 to find the mass of the hydrogen peroxide, which was 1.2 grams. Next, I used the mole formula, which was N equals M over molar mass, so mass over molar mass, and this allowed me to calculate the amount of moles that we use of hydrogen peroxide. So when I calculated this, I got 0.0353 moles, and then I divided that by 2 because of our mole ratio. When looking at the chemical equation for the decomposition of hydrogen peroxide, one can see that in order to balance, we have a 2 in front of H2O2 and a 2 in front of H2O, but there's just a 1 in front of O2, which we don't need to write. Therefore, I needed to divide this value, the moles of H2O2, by 2. I then got 0.01765 moles, and I was then able to use that value in the PV equals nRT formula. Using this formula, I was able to isolate for V, as that was the variable that I was looking for. So I plugged in the moles that I calculated in the previous step for N. For R, I used the gas constant in ATM, and for temperature, I used Kelvin, as the gas constant is in Kelvin. And in order for these units to cancel out, I needed to have temperature in Kelvin as well. So the initial temperature was 22 degrees Celsius, and when I convert that to Kelvin, I add 273, and I get 295 Kelvin. And I divided that by 1 ATM, as my gas constant was in ATM. So for the final answer, I got 0.4273 liters of oxygen gas released at completion. So that's equivalent to 427.3 mils at completion. So therefore, at the completion of this reaction, just over 400 milliliters of oxygen gas is expected to be released.
Prior to performing the experiment, the goal for this lab was taken into consideration and planned accordingly. The first trial consisted of using beaker A as the control for the experiment. 40 milliliters of 3% hydrogen peroxide was added to a 100 milliliter beaker and was left on the scale to decompose with time. Over 5 minutes, the original mass stayed the same at 88.33 grams. The key purpose of the control is to compare it to trials B through E and observe how the catalyst affects the rate of reaction. We kept a fixed amount of manganese oxide, which acted as our catalyst, and a fixed amount of the reactants, which was hydrogen peroxide. Over the course of 4 trials, 40 milliliters of 3% hydrogen peroxide and 0.25 grams of manganese oxide were used and kept constant. The manganese oxide was added to the beaker containing hydrogen peroxide solution, and the reaction was left to proceed. We also ensured the time was kept consistent by recording the amount of gas released over a span of 5 minutes for each trial. This process continued through trials B through E. As the mass decreased, the new mass and time was recorded in the data table. Once the reactions were completed, each trial decreased by a final amount. Beaker B decreased by 0.03 grams, Beaker C decreased by 0.05 grams, Beaker D decreased by 0.04 grams, and Beaker E decreased by 0.03 grams. The overall average was 0.0375 grams. The concentration of the decomposition of hydrogen peroxide results in an exothermic reaction. Each group member was assigned a specific role to ensure maximum accuracy. Samantha's role was to pour the manganese oxide into the beaker, Alessia's role was to record all the data that her group members provided her, Nina's role was to measure the manganese oxide, and Peter's role was to measure the hydrogen peroxide. In assigning these roles, we were able to anticipate minimal human error. The precision of the trials were high because the same instruments were used and the trials were taken carefully. We completed 4 trials and observed the results, which were all in range and consistent. Due to the fact that we did not have access to a gas syringe, this may have accounted as a source of error, as the gas syringe would have been a more accurate representation of the oxygen gas released. We also chose to use a 100 milliliter beaker as the container where the reaction occurred. This is because this allowed for us to isolate for the catalyst due to the beaker having the least amount of surface area. A possible source of error is the decomposition of hydrogen peroxide. The hydrogen peroxide decomposes spontaneously even though it occurs at a very slow rate. Throughout the course of the experiment, the hydrogen peroxide was left sitting in open air and therefore experienced some decomposition. This would cause the concentration of the hydrogen peroxide to be decreased. A lower concentration of hydrogen peroxide would cause a reaction to occur at a slower rate. This error could have been minimized by using the hydrogen peroxide as soon as it was mixed and not allowing the solution to sit in the open air for an extended period of time. Another possible error could be due to mismeasurements. During the experiment, there is a chance that more hydrogen peroxide was used in some trials compared to others, or there could have been more manganese oxide in some trials compared to others. These errors could have affected the results and made the data less accurate, even by the slightest bit. However, these errors are surely preventable, and only by using more advanced technology can we try to aim for a more accurate set of data.
Based on our observations, we experienced a noticeable difference in the rate of reaction from the control and our various trials. Through our calculations, we found an average rate of decomposition to be 1.25 times 10 to the negative 4 grams per second for trials B through E, which reacted with a catalyst. Compared to our control, this is a very noticeable change since our group could not determine the rate of decomposition of stock hydrogen peroxide since it decomposes very slowly on its own. Because the decomposition of the control on its own is so minuscule, it is safe to assume that the rate of catalyzed reactions increased by over 100%.